We're going to start with a question today. I've got this octopus hung from a spring, and it's motionless. It's just sitting there. Question for you. What is the net force on the octopus? We'll give you some choices. And you know the acceleration is 0. There's no motion, and the velocity is 0. The acceleration is 0 as well because the velocity is 0 and it's staying 0. And if the acceleration is 0, Newton's second law tells us that the F in F equals ma is equal to 0. Well, if the F in F equals ma is equal to 0, that force is the net force. So there's no net force on this octopus. But does that mean there is no force acting on it? There's no net force on it, but does that mean there is no force acting on it? We'll give you some choices. And you know the answer to this question as well. There are forces which are acting on this octopus. Think about this. You know the ones that are acting. There's definitely a weight force which is pulling down. Well, there's also a force which is pulling up, and it's the spring force. Okay, so there are forces which are acting on it, but the net force is equal to 0. Tell me what that allows you to say about the magnitude of the weight force and the magnitude of the spring force which is pulling up. What can you say about the magnitude of the weight force and the magnitude of the spring force? We'll give you some choices. Lots of questions today. We want to show you, you're already familiar with the first piece of this chapter because you know the weight force is pulling down, the spring force is pulling up, and if this isn't going anywhere, the acceleration is equal to 0, those two forces must be equal in magnitude. The weight force pulls down, the spring force pulls up, they're equal in magnitude, the net force is equal to 0. If we sum these two force vectors, they sum to 0. The net force is 0, the acceleration is 0. This is an example of what's known as static equilibrium. But something doesn't have to be stationary to be in equilibrium. Let's look at an example. I've got these hover pucks here, and if I open up the valve so air comes out of the balloon, I've got a cushion of air, and this puck rides on a cushion of air. And then if I push it, it slides to the side at a constant speed. And we can tell it's a constant speed if we do a motion diagram. We'll do a motion diagram of the puck moving to the side. And what we see is its motion with constant speed. Well, if the speed's constant, the direction is constant, the velocity is constant, and if it's constant velocity, the acceleration is equal to 0. And if the acceleration is equal to 0, that tells us that the net force is equal to 0 as well. This is an example of what's known as dynamic equilibrium. That's an example of dynamic equilibrium. The heart of Chapter 5 is looking at the connection between force and motion. Now, we've been studying motion, and now we're going to connect it to the forces that cause that motion. Here's a car, and it's got a spring in it, and if I roll it backward, I can get energy stored in the spring, and if I let it go, the wheels will go forward, the car will go forward. When I let it go, there's a force that will make the car accelerate, and it's going to accelerate to the right down the board. And we know, in fact, the force that causes the car to accelerate is the friction force between the tires and the surface of the table. We know that. But I'm going to let it go. We'll do a motion diagram and watch the motion of the car as it goes down the board. And in that case, the car accelerated down the board. Given the direction of the acceleration, we're going to ask you a question. What's the direction of the net force on the car? We'll give you some choices. Well, you know the acceleration is determined by the net force. And so if the acceleration is to the right, the net force is to the right. And in this chapter, you learn how to make free body diagrams for problems like this. We're going to represent the car as a dot. Think about the forces that act on it. There's a weight force which is directed down. There is a normal force which is directed up. And there's a friction force which is directed to the right. The normal force and the weight force are equal to each other. And so when I add those, they cancel. Net result is the net force is just equal to the friction force, which points to the right, and a friction force pointing to the right causes the car to accelerate.